Question B2. This question is about the de Broglie hypothesis. State the de Broglie hypothesis. Now, de Broglie stated that all particles have an associated wavelength. So you can calculate the wavelength of any moving particle. So, and the formula that we have, this is the de Broglie hypothesis formula, that your momentum, your P, is equal to h over lambda. Now, you'd need to explain what this is, where this is your momentum, the momentum of the particle. This is the associated wavelength. The associated wavelength. And this over here is Planck's constant. Remember, whenever using a formula as a definition to explain something, you need to always write out what those are. So determine the de Broglie wavelength of a photon that has been accelerated through a potential difference of 1.2 kilovolts. So this is a proton, not an electron, so it's important to realize. So we've got here, we want to work out the wavelength, so we're going to be using this formula over here, so that lambda is equal to h over p. Now this over here is your momentum. Now we use, because we know the actual energy of this proton is going to be 1.2 kV. That's the energy. When we multiply that by E, we actually get the energy. So the energy, the kinetic energy of this proton is going to be 1.2 times 10 to the 3 volts times 1.6 times 10 to the negative 19 joules. That will give the kinetic energy. Now, we use this, that Ek is equal to a half mv squared, and I change that to equal Ek is equal to m squared v squared over 2, which is equal to 2m, which is equal to p squared over 2m. So your p squared is equal to 2mev, like that, or we take the square root. So in working out the wavelength is going to equal your h over your p, which is equal to 2me, Ek. This is not an EV, this is your kinetic energy. That's that over there is equal to your Ek. Now, when I put this in, this over here, you need to put, this is your mass of a proton. So you go to the front of the data booklet, and where you've got all your constants. This is this value over here. That is that value over here, and obviously it's 2, and this is Planck's constant. When you put that all in, you should get 8.3 times 10 to the negative 13 meters. Okay. And then explain why a precise knowledge of the de Broglie wavelength of a proton implies that the position cannot be observed. So with this over here, we're going to be using these formulas over here, which is Heisenberg's uncertainty principle. Now we're going to specifically use this one over here. So this is the change in x over the change in p, or your uncertainty in x and your uncertainty of p must be greater than equal to h over 4 pi. Now, if we know this, if this is known precisely, as it says over here, a precise knowledge, so this tends to go to 0, or goes close to equal 0, then your position, how much we know about our x value, is going to be greater than equal to h over 4 pi divided by your change in p. And as this goes towards zero, as that goes towards zero, this whole value becomes big, or it tends towards infinity. So it means that your position cannot have, this tends to infinity. So what the Heisenberg uncertainty principle basically states is that the more you know about the momentum, the less that you know about the position. And the same here, the more you know about the energy, the less you'll know about the time that's involved.